friends, welcome to this lecture. In this lecture we will continue our discussion of existence and uniqueness theorem for nonlinear problems. Here we have discussed this. Before we do anything with these successive approximation, we must show that they are defined properly. This means that in order to define yj on some interval I, we must first know that the point s comma yjs remains in the rectangle R for every s in I. So, we have already defined the successive approximation, and we also discussed the ellipsis condition of the nonlinear function f, and with the help of this lemma we want to show that whatever approximation we have constructed, they belongs to the rectangle R. So, before we do anything with these successive approximation, we have already constructed the successive approximation, and we have also considered the definition of ellipsis condition. We must show that they are defined properly. So, it means that we have to first show that the iteration which we have constructed, they are defined properly, and this means that in order to define yj on some interval I, we must first know that the point s comma yjs remains in the rectangle R for every s in I. So, first we have to show that all the iteration belong to the same rectangle for all the time t in that particular interval I. So, that we want to see. So, for that we have a lemma 4. So, choose any two positive numbers a and b, and let R is defined this. R is a set of all t y belonging to R2 such that t is lying between t naught to t naught plus a, and modulus of y minus y naught is less than or equal to b, be the rectangle, and we can compute the maximum of modulus of f t y in this rectangle R, and we can set h as minimum of a and b by m. Then modulus of y and t minus y naught is less than or equal to m t minus t naught for all t belonging to t naught plus h, where h is minimum of a and b by m. So, what we mean by this lemma 4? It means that this lemma states that the graph of y and t is sandwiched between the lines y equal to y naught minus m t minus t naught. You can say open this, if you look at this, it is what y and t minus y naught is less than or equal to m t minus t naught. If you open this, you can say that y and t is lying between y naught minus m t minus t naught and y naught plus m t minus t naught. That we can easily see like this. Here modulus of y and t minus y naught is less than or equal to m t minus t naught. Okay. So, we can write it y and t minus y naught less than or equal to m t minus t naught and greater than equal to minus m t minus t naught, and you can put y naught here. So, y and t is lying between m t minus t naught plus y naught, and here it is y naught minus m t minus t naught. So, we can say that this y and t is lying between this line and this line. That is what we wanted to show it here, that the graph of y and t is sandwiched between the lines y naught minus m t minus t naught and the line y naught equal to y naught plus m t minus 2 naught, and here this is true for all t between t naught to t naught plus h, and these lines leave the rectangle R at t equal to t naught plus a if a is less than b by m, and t naught plus b by m if b by m is less than a. If you look at by showing this, if you look at here, here we already know that t minus t naught is less than h, right. So, it means that we can say that y and t minus y naught is less than or equal to m h, right, and h is what we have defined is minimum of a and b by m, right. So, it means that we can say that if a is minimum, we can say that it is m a, and this is nothing but m b by m, that is less than or equal to b. So, it means that modulus of y and t minus y naught is less than or equal to b. It means that your y and t remains in the rectangle, but if minimum of a and b by m is b by m, we can simply say that y and t minus y naught is less than or equal to m, h is you can say that h is b by m. So, it is less than or equal to b. So, it means that for this h your y end will always remain in the rectangle R, that is what we wanted to show here. So, it means that therefore, the graph of y and t is constrained in R for t naught for t between t naught to t naught plus h. Here h is a minimum of a and b by m. So, this proof we can do by induction on n. So, observe that this is true for n equal to 0. In fact, for n equal to 0 y 0 t is nothing but y naught. So, this is trivially true. So, this is obviously true for f for n equal to 0 because y naught t is equal to y naught. Next, we must show that this condition is true for j plus 1 if it is true for j. So, that we want to show that if we assume yj minus y naught is less than or equal to m t minus t naught, then we want to show that modulus of yj plus 1 t minus y naught is also less than or equal to m t minus t naught. So, for that let us calculate this quantity modulus of yj plus 1 t minus y naught is equal to t naught to t f of s yj s ds. Now, here we already know that this yjs belongs to the rectangle. So, it means that this s yjs belongs to the rectangle, and we already know that in this rectangle your f is bounded by m. So, we can say that this this thing is bounded by this, and here we already know that this is bounded by m. So, we can say that m integration from t naught to t ds. So, which is giving as m t minus t naught. So, it means that modulus of yj plus 1 t minus y naught is less than or equal to m t minus t naught for all t lying between t naught to t naught plus h, and hence we can say that by induction this is true for all n. So, it means that this successive approximation will remain in the rectangle which we have defined like this. So, it means that all the constructed sequence will be in this rectangle R for all time t between t naught to t naught plus h, and in this rectangle your modulus of f t y is bounded by this m. So, we have shown that our with the previous lemma that all the successive approximations satisfy this equation inequality 13. So, it means that all y and t belongs to this rectangle R. Now, we consider the question which is very important question, that convergence of y and t. So, we show that the Picard iteration y and t of 1 converges for each time t in the interval t naught to t naught plus h if dev by dev exists and is continuous. We may replace this condition dev by dev exists and is continuous by the Lipschitz condition also. So, our first step is to reduce the problem of showing the sequence of function y and t converges to much simpler problem of proving that an infinite series converges. So, this we can do by showing the equivalence between y and t and an infinite series. So, here we if you look at, we can write y and t as y naught t plus y 1 t minus y naught t plus 1 y and t minus y n minus 2. So, we can write y and t as the following sum. So, here we can say that clearly this sequence y and t converges if and only if the infinite series n from 1 to infinity modulus of y and t minus y n minus 1 t converges. In fact, if you look at, this means what? This means what? That limit n tending to infinity y and t is going to be what? Limit so y naught t plus summation n equal to 1 to infinity y and t minus y n minus 1 t. So, it means that limit exists provided this series is convergent series. So, to prove the convergence of this y and t, it suffices to show that summation n equal to 1 to infinity modulus of y and t minus y n minus 1 t is less than infinity. So, we need to show the convergence of this infinite series. So, this is done in the following manner. So, modulus of y and t minus y n minus 1 t, let us calculate this quantity, and it is coming out to be t naught to t f of s y n minus 1 s minus f s y n minus 2 s ds. and this is further less than t naught to t modulus of fs yn minus 1 s minus fs yn minus 2 ds ds. Now, here we can apply either the Lipschitz condition or the mean value theorem, such that this is going to be less than or equal to modulus of del over f by del y at some point s xi s into modulus of yn minus 1 s minus yn minus 2 s. So, here at this point either you use mean value theorem or you use the Lipschitz condition, and we can show that here particular if we are using this mean value theorem, we can say that this xi s lies between yn minus 2 s and yn minus 1 s, and from the above lemma which we have just proved, it follows immediately that this point lies in the rectangle R for this. So, it means that if this point lies in this rectangle R, it means that this is bounded by the constant k here, right. If you use the Lipschitz condition, then this is bounded by the Lipschitz constant k here. So, if we are using the Lipschitz condition, from here we can directly move to this. If we are using the boundedness of partial derivative here, then we use this condition that s xi s lies in this rectangle, and in this rectangle this is bounded by k. So, here we can say that from this we can say that modulus of yn t minus yn minus t is less than or equal to k times t naught to t modulus of yn minus 1 s minus yn minus 2 s ds. So, what we do, we are able to get a recursive relation in terms of yn minus t yn t minus yn minus t, and here t is lying between t naught to t naught plus h. Now, here k right now we are assuming the maximum of this quantity over the rectangle R. So, here we have defined k. If we are using the Lipschitz condition, then we can say that k is a Lipschitz constant. So, here for if you look at the recursive relation, this yn t minus yn minus 1 t less than or equal to k t naught to t yn minus 1 s minus yn minus 2 s for say n equal to 2. So, let us define it for n equal to 2. So, it is y2 t minus y1 t is less than or equal to k t naught to t y1 s minus y naught s ds, and we already know that by approximation, if we already know that approximation, when we consider approximation, y1 t is equal to y naught t plus t naught to t f of s y naught s ds, and we already know that y1 t minus y naught is bounded by t naught to t modulus of f of s y naught of s ds, and this is, we already know that this is bounded by m. So, m, and this is what, t minus t naught. So, we already know that this y1 minus y1 s minus y naught s is bounded by this quantity. So, we can say that this is bounded by k m t naught to t s minus t naught. Here y1 t minus y naught, we are bounded saying that it is bounded by this quantity. So, y1 s minus y naught s is bounded by s minus t naught, and if you simplify this integration, then it is coming out to be k m t minus t naught square divided by 2. So, now this we have shown for n equal to 2. Now, we can also say that y3 t minus y2 t is less than or equal to k times t naught to t y2 s minus y1 s ds, and we just now we have calculated the bound for this y2 s minus y1 s, that is this we have just calculated that it is bounded by k m t minus t naught square divided by 2. So, using this bound we have we can write it m k square t naught to t s minus t naught square divided by 2 ds, and when you calculate this, it is coming out to be m k square t minus t naught to power 3 divided by factorial 3. And if we proceed like this, and we can show that by induction, we can show that modulus of yn t minus yn minus 1 t is less than or equal to m k to power n minus 1 t minus t naught to power n divided by factorial n. Here t is lying between t naught to t naught plus h. So, we can show that this series which we are considering, that modulus of y1 t minus y naught t plus y2 t minus y1 t and so on is less than or equal to y1 t minus y naught t is bounded by m t minus t naught, and y2 t minus y1 t is bounded by this quantity, and so on. We can say that yn t minus y1 minus 1t is bounded by this, and if you take the summation here, we since t is lying between t naught to t naught plus h, so t minus t naught is bounded by h, so we can say that this is further bounded by mh plus mk h square divided by factorial 2 plus mk square h cube upon factorial 3, and so on. And here if you look at, this is a kind of known series, and we can make that say form by multiplying by k and divide by k. So we can say that m by k then it is written as kh plus kh whole square upon 2 upon factorial 2, and so on. And if you look at, this is an exponential series, and we can write that this is written as m by k e to the power kh minus 1. So we can say that this series is a finite series. So we can say that this series is bounded by some finite quantity, and we can say that it is less than infinity. So we can see that yn t converges for all t belonging to t naught to t naught plus h. So we have shown that this series is finite. So it means that yn t is basically what? Yn t is y naught plus summation n equal to 1 to infinity yn t minus y naught yn minus 1 t, and we have shown that this part is finite. So adding this y naught is keep this quantity finite. So we can say that yn t converges for all t belonging to t naught plus h, and since it is convergent, we say that limit is yt. So yt is given as the limit of this infinite series. So now we want to show that yt satisfy the initial value problem. So what we have done first two steps. First step is the definition of successive approximation, we have done in previous lecture, and then we have to show that this approximation converges to some limit. So that we have just shown that the sequence yn t converges to some limit, call it yt, and now we want to show that this limit satisfy the initial value problem. So it means that it satisfies the equation yt equal to y naught plus t naught to t fs ys ds, and we also want to show that this yt is continuous, right. So by showing that yt is a solution of integral equation, and we can show that it means that yt satisfy the initial value problem as well. So to show this, let us recall the equation yn plus 1 t equal to y naught plus t naught to t fs yns ds. Now if you apply the limit here, then limit will be what? Since limit of yn plus 1 t is yt, so we can say, and y naught is independent of n, so we can say that if we take the limit, it is given as yt equal to y naught plus limit n tending to infinity t naught to t fs yns ds. And to show that this right hand limit is going to be equal to this quantity, we must show the following thing, that modulus of t naught to t fs ys ds minus t naught to t fs yns ds is tending to 0 as n tending to infinity. So it means that we have to show that this is nothing but this quantity, right. So this we want to show here. So how we can show? Again we can prove this by observing that first of all that this yt lies in the rectangle R. Since every yn t is lying in this rectangle R, it means that here we know that yn t minus y naught is less than or equal to m t minus t naught, and if you take the limit n tending to infinity, we can say that this implies that yt minus y naught will also satisfy the condition t minus t naught. So yt will also belong to the rectangle R. So now look at this quantity, modulus of t naught to t fs ys ds minus t naught to t fs yns ds. So so it is further less than t naught to t modulus of this quantity, and here we can apply either the Lipschitz constant, Lipschitz condition, or say boundedness of partial derivative of f. We can say that this is less than or equal to k times t naught to t ys minus yns ds. Now since here we have assumed that y belongs to y lies in rectangle R. So it means that to find out this bound of this, we have to look at the quantity of this. So, here what is ys? Ys is y naught plus j equal to 1 to infinity yjs minus yj minus 1 s, and yns is defined as y naught plus j from 1 to n yjs minus yj minus s. So, using this expression, these two expression, we can find out ys minus yns as follows. So, y modulus of ys minus yns is given as j from n plus 1 to infinity yjs minus yj minus 1 s. Now, we want to show that this quantity can be made arbitrary small as n tending to infinity. So, we can see that modulus of ys minus yns less than or equal to m j from n plus 1 to infinity kj minus 1 s minus t naught to power j upon factorial j. Here for this particular step we are using the bond of yjs minus yj minus 1 s. So, here we are showing that this is further less than or equal to j from n plus 1 to infinity modulus of yj s minus yj minus 1 s this thing, and we already know the bound of this. The bound of this is k to power j minus 1 s minus t naught to power j divided by factorial j here. So, now again we can simplify this. This s minus t naught is bounded by h. So, we can write this as m j from n plus 1 to infinity k to power j minus 1 s to power j upon factorial j. Again we can multiply by k and divide by k, and we can write m by k j from n plus 1 to infinity k h to power j upon factorial j. If you look at this is what, this is the tail of the series e to power k h, right, k h minus 1. So, this is the tail of the series of e to power k h minus 1, and we know that since this series is convergent, it means that as n tending to infinity this tail is tending to 0. So, it means that as n tending to infinity modulus of ys minus yns is also tending to 0, and this implies that this is also tending to 0. In fact, we can write this as modulus of t naught to t fs ys ds minus t naught to t fs yns ds, which is bounded by this quantity m j from n plus 1 to infinity k h to power j upon factorial j t naught to t ds, and we can write it like this, and we know that this is tending to 0 as n tending to infinity, and hence we can say that limit n tending to infinity t naught to t fs yns ds is equal to t naught to t fs ys ds, and we can say that this implies that yt satisfy the integral equation 19. So, we have shown that yt satisfy the integral equation. Now, we want to show that yt is a continuous function. So, this we can achieve by Weierstrass-M test. In fact, while proving the convergence part, we have observed that the series j from 0 to infinity yj plus 1 t minus yjt is uniformly convergent series in the interval t naught to t naught plus h. So, how we can say that? If you look at the convergence part in view of the definition of this yj plus 1 t minus yjt, this implies the absolute convergence on t naught to t naught plus h of the following series. We can remember this is what modulus of yj plus 1 t minus yjt is bounded by, if you look at this is bounded by the following thing kj minus 1 s minus t naught to power j upon factorial j here. So, this is bounded by this k to power j h to power j minus 1 upon factorial j minus 1. Is it okay? I think it is here. This is just a minute. So, here it is j here, and here it is j here. So, we can say that that this is bounded by kj plus 1 s to power j upon factorial j. Now, we can apply Weierstrass-M test, and we can say that we can call this as mj, and we can say that summation of mj is converging. So, this series is convergent. So, we can say that by Weierstrass-M test this is convergent, and this convergence is uniform convergence. So, we can say since yjt equal to y naught t plus m from 0 to j minus 1 ym plus 1 t minus ymt, this also proved the convergence of the sequence yjt for every t in the interval t naught to t naught plus s to some function of t which we call as yt. Now, we know that each yn is a continuous function and convergence to y is uniform. So, we can say that limit function is also a continuous function, right. So, we need to observe only this thing, that the convergence which we have discussed is a uniform convergence, and each y and t is basically, if you look at yj t is basically what it is, sum of these things, and each component is a continuous function. So, we can say that it will converge to a continuous function. So, we can say that yt is a continuous function. So, if we summarize the discussion which we have done today, we can say that we have proved the following theorem, that let f and double f by double y be continuous in the rectangle R, where R is defined as the set t and y defined as that t is lying between t naught to t naught plus h, modulus of y minus y naught is less than or equal to b, and we can compute the bound m, which is minimum of a and b by m. Then the initial value problem y dash equal to f t y, y t naught equal to y naught has at least one solution y t on the interval this t naught to t naught plus h. So, this theorem guarantees that there exists at least one solution, and we can also use a similar argument to show that the solution exists for some interval t less than or equal to t naught in a same way. And now we want to show that not only it has a one solution, but it has a unique solution. So, we have assumed that double f by double y be continuous in this rectangle. That condition is sufficient to show that the solution is unique as well. To show the uniqueness part, let us consider the following thing. So, in this we want to prove that solution is unique. So, earlier theorem guarantees the existence of at least one solution. So, it means that we have one solution of this. Now, to show that it has a unique solution, let us assume that we have one more solution, call that as zt. So, let zt be another solution of the above differential equation. So, it means that yt is a solution means this equation is true, zt is a solution means this equation is also true. Now, with the help of this we can consider modulus of yt minus zt, and it is coming out to be, if you look at modulus of yt minus zt is less than or equal to modulus of t naught to t f of s y of s minus t naught to t f of s z of s ds. Now, here either we can use the existence of double f by double y, or say Lipschitz condition on f. We can show that modulus of yt minus zt is less than or equal to k times t naught to t modulus of ys minus zs ds. So, here we can say that in fact this is equality. So, we can say that modulus of yt minus zt is less than equal to modulus of t naught to t fs ys minus fs zs ds. Now, here we can apply the Lipschitz condition or the bound of the partial derivative of f. So, here we can say that modulus of yt minus zt less than or equal to k times t naught to t ys minus zs ds. Now, we want to show from this inequality that yd is ideally equal to zt. So, this we can show by saying that yt minus zt is ideally equal to 0, that is yt equal to zt. So, we want to show that this yt minus zt is basically 0. So, we want to prove that let wt is non-negative, and for every t with the wt satisfy the following inequality, that wt is less than or equal to k times t naught to t ws ds, then we want to show that wt is equal to 0. So, here if you simply want to prove like this, then we can simply differentiate this like w dash t is less than k wt, and this we can write it and w dash t minus k wt less than or equal to 0, and this I can write it d by dt of e to the power minus k t wt less than or equal to 0, and if we integrate by integrate from t naught to t, we can write it e to the power minus k t minus t naught w t less than or equal to W T naught, and we already know that this W T naught is 0 because here we have just calculated here W T naught is 0. So, we can write it this as W T is less than or equal to 0, or you can if you do not want to do it like this, then we can simply say that since d by dt of e to power minus k t W T is less than or equal to 0, and this if we integrate, we can simply write from 0 t, we can simply write this as the following. We can simply say that e to power minus k t W T less than or equal to e to power minus k 0 W of 0, and we can simply say that this implies that W T is less than or equal to this is W 0 e to power minus k t, and we can say that W 0 is 0. From this we can show it here that W 0 is less than 0. So, we can say that W T is less than or equal to 0, and we are done, right. So, either you, but the problem is that I cannot use this, okay. Why? Because I cannot differentiate this directly, right. So, to avoid this direct differentiation, what we do, we let us assume this right hand side as a new function u t. So, let u t is from t naught to t W s ds, then we can differentiate this and we can find out du by dt as W T, right. So, and W T we already know that it is bounded by k times t naught to t W s ds. So, it is less than or equal to k times t naught to t W s ds, and by the definition of u t I can say that this is nothing but k u t. So, du by dt is less than or equal to k times u t, and this implies that e to power minus k t minus t naught u t is less than or equal to u t naught, and we already know that u t naught is what? U t naught is given as 0, because if you put t equal to t naught, then it is nothing but 0. So, it means that e to power minus k t minus t naught u t is less than or equal to 0. Now, this is a never 0 value. So, it means that u t has to be bounded above by 0, and we already know that u t is positive. So, it means that u t is equal to 0. So, it means that what we have proved here that u t is 0, and now this is possible only when W t is 0. So, it means that what we have proved that if W t is non-negative function along with this inequality, then we can show that W t is equal to 0 only. So, how we are going to utilize this lemma in our result? Here we have shown this that y t minus z t modulus of y t minus z t is less than or equal to k times t naught to t modulus of y s minus z s d s. So, here you can assume W t is equal to modulus of y t minus z t. So, if we assume this, then it is written as W t is less than or equal to k times t naught to t W s d s, and just now we have proved this lemma that this implies that your W s has to be 0. So, it means that 0 less than or equal to W t. Now, W t is less than or equal to k times t naught to t W s d s, which is nothing but k times u t, and u t is coming out to be 0. So, it means that 0 less than or equal to W t less than or equal to 0. So, this implies that W t is equal to 0. Now, what is W t here? W t is defined as modulus of y t minus z t. So, it means that y t is equal to z t. So, what we have proved? We have proved the uniqueness of the solution. So, in this lecture, what we have shown here that the this first we have shown that this y dash t equal to f t y t with the condition y t naught equal to y naught. This is equivalent to the integral equation y t equal to y naught plus t naught to t f of s y of s ds, and then we have constructed the approximate solution of this integral equation, and we have shown that the approximation sequence of approximation converges to a limit y t. We have shown that y t is continuous, and we have shown that such a y t it means that y t is a solution, and we have shown that a solution which satisfies the integral equation is going to be unique solution. So, what we have shown that if f is continuous and satisfy the Lipschitz condition in a rectangle R, then f has to be then initial value problem has a solution. So, that is what we have stated as theorem 5, that let f and del f by del y be continuous in the rectangle R, where R is defined as t from t naught to t naught plus h, modulus of y minus y naught is less than b, and we can compute m as minimum of a and b by m. Then the initial value problem y dash equal to f t y, y t naught equal to y naught has at least one solution y t on the interval t naught to t naught plus h, and we can also, we have shown that it has a unique solution. So, that is the content of today's this lecture. We will continue in next lecture in this theory. Okay. Thank you for listening us. Thank you.